presentation. So the learning objects of today's video is you will know how to implement different types of digital gates using CMOS technology, and you will learn about stick diagrams. So what are the universal gates in digital circuits? We know that NAND gate and NOR gate. And why we call them as universal gate means using these two gates, we can design any gate. That's why we call it as NAND universal gates. So before going into the implementation of digital circuits, let's deal with switches. Now, when I connect switches in series, like here I have shown, I will get output when my inputs both A and B are high. When I connect switches in parallel, I will get my output high when any one of my input A or B will be high. So from this, we are seeing here that if we want to get AND operation, we have to connect the switches in series. Whereas if we want to get OR operation, if we connect switches in parallel, we are able to get OR operation. So why we prefer using why we prefer CMOS technology rather than NMOS or PMOS? There is a reason, because NMOS technology, when we use, it will give you strong 0, but it won't give you strong 1. Whereas for PMOS, it will give you strong 1, but it won't give you strong 0. Now, in CMOS technology, we use both PMOS and NMOS to get strong 0 and strong 1. So for this network is known as pull down network, and upper side network is known as pull up network. We design pull down network using NMOS, and we design pull up network using PMOS. So here's the example. Here's the diagram for inverter. Now let's see how we get inverter using CMOS technology. Now inverter means when we give input, the output should be inversion of the input. So here, let's say I have given input as V in. Now my output will be V in bar. So in this way, we implement CMOS inverter. This NMOS will be high when V in is high, and PMOS will be turned on when V in is 0. Now let's see how to implement NAND gate using CMOS technology. Here for NAND gate, let's say we have taken 2 input NAND gate. Let's say my inputs are A and B. The Boolean expression for NAND gate is Y is equals to A into B bar, 4 bar. So now we have seen in the switches, if we want to perform AND operation, we have to connect the switch or NMOS in series. So we have connected our NMOS as in series, and PMOS is just dual of NMOS. So we just take dual of NMOS. So this network is known as pull down network, and this network is known as pull up network. Why this network is known as pull up network means when this network is high, we get VDD is connected to, VDD will be connected to output load. When my pull down network is turned on, then my output will be discharged using this path. So my output will become 0 and grounded. Similarly, for 3-input NAND gate. The Boolean expression for 3-input NAND gate is y is equals to a, b, c whole bar. So in the similar way, we connect all the NMOS transistors in series, and PMOS, we just take dual of NMOS. So in this way, we get 3-input NAND gate. Now, 2-input NOR gate. The Boolean expression for 2-input NAND gate is a plus b whole bar, and to perform OR operation, we connect the NMOS in parallel, and we just take dual of NMOS network to construct PMOS network. So in this way, we are able to create our 2-input NOR gate using CMOS technology. Now, take a minute and implement 3-input NOR gate by yourself. Now let's see for some general expressions. Here I have taken Boolean expression as AB plus CD whole bar. Now this term is product term, this term is product term, and these two are summed. So AB should be in series, A and B. Now CD, these two terminals are connected in series using NMOS. Now for PMOS implementation, we just take dual of this NMOS network, and now A, B are in series. Now we connect them in parallel, A, B. Now CD are in series. Now we connect them in parallel. Now these two circuits are in parallel. Now, so we connected them as series cascaded. So in this way, we can obtain our required Boolean expression. And if you want to get A equal to AB plus CD, we have to connect here one NOT gate. This one NOT gate. Now let's see one more expression. A plus B into C plus D. Now C and D are in summation, so we connected them in parallel. Now C plus D is product with B, so we connected them in series. Now this is one term, let's say. So this is one term and this is one term. Now we are adding these two terms, means we have to connect this network and A in parallel. So we connected this network and this transistor connected to A in parallel. So in this way, we constructed our pull down network. And now for PMOS pull up network, we just take dual of NMOS network. See, this transistor and this network is in parallel, so we connect them as series first. Now B and CD are in series, so we take B and CD in parallel. Now CD are in parallel, we just take CD in series. Now let's see how to draw stick diagrams for our implemented digital gates. Now using CMOS technology, we constructed our digital gates. Now for representation purpose, we use different color codes to just represent our circuit in the form of different lines. Now we represent metal with blue color and P diffusion with yellow and N diffusion with green and polysilicon with red color. Now we implemented our NOT gate using CMOS technology. This is my PMOS and this is my NMOS, and output will be inversion of my input. Now my PMOS can be represented by using yellow color and my NMOS can be represented by using green color. Now polysilicon gates, this is gate. So gate is represented by using red color. These are connections. For different connections, we use metals as blue color. Now when N diffusion layer crosses red polysilicon layer, it will create my NMOS. I assume that. When P diffusion layer crosses polysilicon layer, then PMOS will be created. Like we have shown here. This is my polysilicon layer. This is my P diffusion. This is my N diffusion. And this is my polysilicon. So when these two at this interference, we got one NMOS, and here I got PMOS. So in this way, we represent our NOT gate using different color codes. Now let's see for another way. For NOR gate, see here for NOR gate, two input NOR gate, I have two inputs A and B. So I have to get two NMOS transistors and two PMOS transistors. So I have mentioned my VDD and ground with blue color, and N diffusion with green color. These are different color codes we use in stick diagrams. And for P diffusion, I represented this by using yellow color. Now this red is my polysilicon layer. So when my red means polysilicon layer interface with P diffusion or N diffusion, it will create PMOS or NMOS. So now let's see. For PMOS, we have the upper terminal is source and lower terminal is drain. For NMOS, the upper terminal will be drain and lower terminal will be source. So my first input source is connected to PDD. So I connected my first input source to VDD, and the drain of A and the source of B are connected. So the drain of A and the source of B are connected. And the drain of my input B is connected to output. So I connected using this. Similarly for NMOS, let's see for NMOS. Now the drain of A and the drain of B are connected. This is drain, this is source, this is drain, this is source. So the drain of NMOS and the drain of NMOS the drain. These two drains are interconnected, and the source of A and the source of B are grounded. So we connected the source of A and source of B to grounded. In this way, we got stick diagram for an NOR gate. Now let's see for 3 input NAND gate. Now I hope that you can draw stick diagram for 2-input NAND gate. So do by yourself, and let's see for 3-input NAND gate. My Boolean expression for 3-input NAND gate is y is equals to a, b, c whole bar. So all are these connected in series. Now, similarly, I have drawn here VDD, my ground. This is N diffusion layer. This is P diffusion layer. Now I have 3 inputs. So I have 3 gates. 1, 2, 3. So I mentioned here A, B, and C. When polysilicon layer intersects P diffusion or N diffusion, it will create my PMOS or NMOS. Now, the sources of all my PMOS transistors are connected to VDD. So let's see. This is my source of A. This is source of B, source of C. So all these are connected to VDD. Now, the drains of all my PMOS transistors are connected to output. So the drain of, sorry. So the drain of A and the drain of B and drain of C are connected to output. Now let's see for NMOS network. This network is known as pull down network. The drain of A is connected to, this is drain, this is source. So the drain of NMOS transistor is connected to output, and the source of A and the drain of B are interconnected. Source of A, drain of B are interconnected. Then my source of B and the drain of C are interconnected. So source of B and the drain of C are interconnected, and my source is grounded. So this is, sorry, I forgot to draw here. So this is grounded. So my source is grounded. Now let's see for common Boolean expression. How to draw stick diagram for common general Boolean expression. Now let's see. Now I have taken one Boolean expression as A plus B into C plus D. Now I have 3 inputs A, B, C, and D. So similarly for VDD, for ground, we represented using blue color. For N diffusion, I represented by using green color, and P diffusion I represented by using yellow color. And since I have 4 inputs, I drawn 4 polysilicon layers. 1, 2, 3, and 4. Now, for PMOS, the first terminal is source and lower terminal is drain. So the source of B is connected to VDD. Source of B and source of C is connected to VDD. So source of C, source of B are connected to VDD. Now, this is source, this is drain. This is source of C, D, and this is drain of D. Now my CMOS source, sorry, drain is connected to this PMOS, second PMOS source. So the drain of C is connected to source of D. Now the drain, see, the drain of A, this is my source, this is drain. Now the drain of A is connected to output, so I connected my drain as to output. Now let's see for NMOS circuit. Source of A is connected to ground, so I connected it to ground. Drain of A, drain of B are connected to Y. So the drain of A and drain of B are connected to Y. Source of B and the drains of C and D are connected. So source of source of B, drain of C, and the drain of D are connected using this method. Now the source of C and source of D are grounded. So I just grounded here. So I just grounded the source of C and D here. So that's all for today. I hope you learned something new in this video. So thank you.